Okay, so here's the pre-lab for the organic lab on October 27th. Again, my apologies to those of you inconvenienced by starting late for the event on campus. I hope you went, hope you got something out of it. But anyway, on to the lab. So, in today's lab, you're going to make a compound called 4-methyl-umbelliferone. We're going to talk about that and why you'd want to make that. And we're also going to use an immobilized catalyst for the first time. So a couple of notes before I get into the chemistry. Noted over here, if you zoom in. First, we're going to work in pairs today. So go ahead and pair up with someone. You want to set your hot plate to about 100 degrees. The reaction has to get to 80 degrees C. So you want to set the hot plate a little above that. Don't crank it up all the way, but the notes from previous years we have that a lot of times people don't get it hot enough. There are going to be two types of acid beads. We'll talk more about the acid beads here in a minute. But there's Dowex, D-O-W-E-X, and Amberlist. If you can, use Dowex if you have a choice when you get back to the back of the room. Dowex is a little easier to filter out of the reaction. You can get the Amberlist out, it's not a big deal, but if you use Dowex if it's available. And finally, you're going to make a pipette filter. At one point, get TA help from that. It's a little hard to show. It's easy to do. You basically put a little wad of cotton into a pipette and then put liquid through it. But if you're curious about that, or if you haven't seen it before, get your TA to help with that. Okay, so those are the notes. You can rewind that and see it at your leisure. So, like I said, today you're going to make 4-methyl-umbelliferone, which has this structure. Coumarin, 4-methyl-umbelliferone is known as acoumarin. So a lot of times in organic chemistry, what we do is we sort of have a parent structure, in this case coumarin, and then this would be a derivative or an analog of coumarin. And so you can see that coumarin is a benzene ring fused to a pyrrone ring where you have an ester, an cyclic ester, and an unsaturation. So if you think about the structure of this molecule, right, all of these are sp2 hybridized. The two alkene carbons are sp2 hybridized. This carbonyl carbon is sp2 hybridized. You actually have significant resonance, really, where you have delocalization of the electrons there. And that makes this bond fairly planar. If you think about it from an electron counting standpoint, you've got 2 electrons here, 2 there, and then the lone pair 2, and I can draw that out, that resonance structure out. Right. So then this becomes an aromatic ring as well, 2, 4, 6. And so, in a real sense, this is kind of like naphthalene. So naphthalene is 2 fused benzene rings. It's obviously a good bit more polar. So it's a little bit more water soluble, not much. 4-methyl-umbelliferone is a little more water soluble, but again, not much. You're going to filter it. You're going to use water to crash the product out at the end of your reaction. All of these structures, coumarin, 4-methyl-umbelliferone that you're going to make, and naphthalene, do something called fluorescence. They fluoresce well, and you'll see that in the lab. I'm going to go ahead and erase down here. So, when something fluoresces, so if we take coumarin and we shine light on it, all right, that's not very clear, is it? So H nu, you might be familiar with this equation from physics. The energy of a photon is equal to Planck's constant times the frequency of the photon. And so a lot of times in a photochemical reaction, you'll simply see light represented by H nu. So what's going to happen is coumarin is going to absorb a photon. And when a molecule or an atom absorbs a photon, the energy of that photon has to go somewhere. You can't just, you can't just disappear the energy. So what happens is you're going to get something that's going to be called an excited state. Wrong. All right, so this is kind of a weird, you've probably never seen this. This little bracket just means this molecule, and the star means excited state. right? And so put simply, let's take one alkene. Okay, so let's say we just have a pi bond, it's got 2 pi electrons in it. When a photon of light is absorbed, one of these electrons will hop up to the antibonding orbital. Right, so any pi bond, if you think about your bonding, any pi bond is going to have a pi antibonding orbital associated with it. So when visible or ultraviolet light is absorbed by a molecule, an electronic transition takes place. Okay, and by the phrase electronic transition, what we mean is an electron transitions from one orbital to another. And there's a lot that goes on here. I personally study this. It's fascinating. If you're interested in solar energy conversion, you have to think about this a lot. But I'm just going to draw it as this electron just kind of hops up there. And so it's in a different orbital. The spins remain paired. So that's a rule of photochemistry. Is it's very hard to unpair paired spins. And so this is the excited state. And so in a very real sense, you can't really do this with a Lewis structure. That's why we just put this star on there. The electrons are in the same place, but you've really broken that pi bond. Okay, so if I take two, if the pi bond is 2 bonding pi electrons, and now I have 1 bonding and 1 antibonding electron, 1 bonding and 1 antibonding electron is not a bond. So you basically break that, but there's no good way to draw that Lewis structure. And so we just stick an asterisk on it and we say it's an excited state. Okay, so the question is, what happens to the excited state? How do we get back to what we call the ground state? Right? This is how the molecule is going to be most of the time. We never really talk about the ground state that much because the ground state's just the ground state. All right, so there's several different ways to get back to the ground state. Think about what they could do. The excited state could do a chemical reaction. And right, that could be an electron transfer. You've got a low-lying stable orbital that has a hole now. So an electron could come from somewhere else into this orbital. That would get you out of the excited state. This electron's in a high energy orbital, so that could be given away. The excited state can make bonds. The excited state can do an isomerization. But the way I'm going to, today's lab, the fluorescence, one way for us to get back to ground state is to emit a photon. Okay, so minus h nu. So if the excited state emits a photon, that would have let this electron come back down, right? There's an energy gap here. Right, there's an energy gap there, and that energy gap has to equal the energy of the photon. All right, so a molecule can absorb light. You see that all the time. Things have color. So depending on the wavelengths of light, the frequencies of light that get absorbed, things have different colors. And an excited state can emit a photon to come back to the ground state. And you'll see this today. At the end of the lab, you'll be able to use a UV light to make the molecule fluoresce. All right, so that's a question, though. The way I've drawn this, you might say, well, here's the ground state, and it's going to absorb a photon. And here's the excited state, and it's going to emit a photon. These two photons should be the same energy, right? Are you thinking that? Maybe you're not thinking that, but you should be thinking that. So okay, so I'll let you ponder that. These two photons are only going to be the same frequency for atoms. All right, so I'm going to have to erase some of this. I only have so much board that fits on the camera. So I'm going to erase right here. And I'm going to draw something. I'm going to go ahead and erase this as well. I'm going to draw something you won't like, but trust me. Energy, reaction coordinate. I know you've seen these diagrams before. All right, so for a chemical bond, that's, if you plot the reaction coordinate, this is usually a bond distance, say. So we might look at the bond distance between these two carbon atoms. This is for the ground state. It's called an energy surface for the ground state. And you'll also, at some point, somebody probably told you there are vibration levels here. Okay, on up. I guess I should draw them all the way up. Okay, so the molecule the electrons in this bond have to be in one of these levels, right? Quantum mechanics, if you think about the phrase quantum mechanics, the energy of a photon or of a molecule or an electron, they're quantized. Well, here's the tricky bit. Remember, when we go to the excited state, we effectively break a bond. So we break this pi bond. Okay, so if we break that bond, we don't have the same molecule anymore. So this energy surface no longer represents the excited state. And the excited state may look something like this. That's not right. Imagine that's a curve. Imagine I can draw. Okay, so this is the excited state. And again. They're the quantized energy levels. So the most likely place for the ground state molecule to be is sort of in the middle at the lowest vibrational level. And so this, you're not going to be tested on this. I'm really talking because I like to talk about this stuff. But it also explains what you're going to see later today. Okay, so when a molecule absorbs light, the only thing that changes is the electron. An electron is very tiny compared to the rest of the molecule or even a nucleus. And so the electron can move really quick and the rest of the molecule stays static. And what that means is on this is a bond distance, right? The bond is not going to change as soon as the electron is absorbed. So when the photon is absorbed, you just move straight up. You move from this bottom surface to the top, to the excited state surface, straight up. You don't go there. You go straight up like this. The bond distance won't change. When the molecule is absorbed, if the two atoms are this far apart, as soon as you get to the excited state, they have to still be this far apart. That's obviously in a really high vibrational level, and so very quickly the bond will change. And that just gives it away by heat. So you give off some heat, and you go down now to the most stable. So this change, here we have plus light. Here, you give off heat. All right, and that's why when things absorb light, they heat up. If you think about your leather seats in your car, your vinyl seats in your car, it sits out in the sun, absorbs that sunlight, and it heats up. You sit on it and you burn yourself. Okay. Now, when the excited state gives off a photon, same thing is true. It has to go straight down to the surface. Imagine, again, I can draw. Straight down to the surface, so it goes straight to there. All right. And now, so this is minus a photon, and then back down to here, minus heat, gives off a little more heat. Why have I talked about all this? Just assume all this is right. You can rewind and watch it. First photon, big line, big energy gap. Second photon, little energy gap. Okay, so this, it's going to turn out, in our example, this big energy photon, right? More energy, higher frequency, more to the blue. This first photon is going to be a UV photon. The second photon will be a visible photon. Right? So the visible is to the red of ultraviolet. And so this may be blue or green, but it's to the red of ultraviolet. It's lower energy than the emitted photon is lower energy than the absorbed photon. Right? If the energies of the two photons were exactly the same, and that's what you see in atomic spectroscopy, you wouldn't be able to see this. So today, you're going to use a UV light, you're going to excite 4-methylumbelliferone, and you're going to see visible light come out of it. All right. So you get to go, you can go back and look at that. I'm not going to test you on this stuff, but you'll see it. Well, you'll see it in spectroscopy classes down the road. If you ever take PChem or chem analysis, inorganic chemistry. So if you're a chemistry major, this all is very pertinent to you. If you're not a chemistry major, it's cool to know. So that when something fluoresces, it's going to always give off a photon of longer wavelength than it absorbs. All right, so I'm going to erase for a minute. You can fast forward through that. And we're going to talk about immobilized catalysts. So the reaction today is a condensation reaction. And I'm not going to draw the mechanism of that. That's up to you guys. But I will talk about a reaction you might have seen before. How do you want to put this? So just an aldol reaction. Right. So phenyl pH here is an abbreviation for a phenyl ring. So this is an aldol condensation. And this can be acid catalyzed. So this goes through the enol. Man, the whiteboard drawing's not good today. So if we catalyze this reaction with acid, you protonate the carbonyl first on benzaldehyde, and then the enol of acetone would attack that. There's an intermediate, and then you can lose. There's going to be some conjugate base that went with your proton, and that can take that proton off. All right, so that's an acid-catalyzed aldol. You would then, for the condensation, you would then do an acid-catalyzed dehydration. So again, H+. Remember, if you're under acidic conditions, the oxygens are always either going to be protonated or neutral. You're never going to have an O-. You can't have a strong base with a strong acid. And then this thing can just leave. So we lose water, get a cation, and then our conjugate base will take that. Loads of fun. Okay. The reason I go through all that, again, some of it is to remind you that under acidic conditions, you're always going to either have protonated oxygens or neutral oxygens. You don't ever want to have a strong acid and a strong base in the same mechanism. The other reason is, look at this acid, H+. Could be HCl, could be sulfuric acid, could be para-toluene sulfonic acid, but if it's a molecular acid, you have to separate it from your product. At the end, you're going to have this product and it's going to be sitting there with molecular acid. And you have to do an aqueous workup. You guys have done separatory funnel extractions. You have to shake things up, separate layers. It gets very messy. So a better bet, I'm going to erase again, a better bet is to use an acid that isn't molecular. And now, obviously, all materials are molecular, so that's a bit of a misnomer. Okay, so this is the acid I was talking about. Para-toluene sulfonic acid. Sulfonic acid is SO3H. pKa is round about 0, maybe a little less. Toluene is just a benzene with a methyl on it. So para-toluene sulfonic acid. The acid you're going to use today, Dowex, is a polystyrene-based acid. Okay, so to make polystyrene, we take styrene, that's styrene, you've heard of polystyrene, we initiate this